introduction. And hello, everyone, and happy winter solstice and everywhere in the world. We're honored to be invited to speak on my recent research on music AI here. Okay, let me share my screen. Okay, is that okay? Oops. Can you see that clearly?
Yeah, that looks good.
Cool, okay, let's get started. Okay, so the title is Learning Interpretable Music Representations from Human Stupidity to Artificial Intelligence. So just a brief intro that I see my research path mainly be driven by two interests, two passions. On the one hand, I'm a musician, I play flute, I sing, I compose, and I'm really curious how human minds analyze and create music. On the other hand, I'm a computer scientist, and I deeply believe in that the best way to understand musicianship is to recreate it in a human-centered way. And that's why I have been, creating intelligent systems that help people better compose, perform, and learn music. And here, just to give everyone a little bit sense on what kind of interactive system I've been working on, let's just briefly turn the time back to 2015 and see this interactive system between I and the robot. Okay. So I speed up and slow down, and now it's the cadence. Last phrase. You see that the robot is following me with this facial and gesture expression. Slow down, even slower. Okay, so I guess speaking of music intelligence, this system is really, in his infancy and really immature. But I want to share a story when I, work on this project. And by the way, the robot was invented in Waseda University, and at that time I was working on automatic accompaniment system that was invented by Roger 30 years ago. And I just plug in the system to the robot. And when I work on this project, actually, the saxophone player, this robot, can only play 6 tones, and to play accompaniment for me, it needs 9 tones. So I need to debug the system, and I'm not a mechanical engineering guy. And so what I did is I say, do you have an extra saxophone? Because I can play somehow a little bit saxophone. So, okay, yes, we have a saxophone. And I noticed that whenever this robot is hitting an octave higher, there's some bizarre notes, bizarre sound happening. So I was trying to, duplicate its mistake on my saxophone. And finally, I realized that, if I push my fingers in a certain asynchronized way, I can duplicate this bug. And when I, look at what the robot is doing, indeed, it is like this way. So the story is to achieve certain artificial intelligence on the robot, what I'm doing here is kind of self-reflection and human stupidity. If you look carefully here, because I'm not a mechanical engineering guy, so I have a quick fix. You can see there's a rubber band here. So I kind of attach a rubber band here to fix that hole. That valve is kind of fixed. so that the robot can play the tones. All right, so that's the story. And after this demo, naturally people ask, okay, is the score given? I say yes, the score is given because it's traditional accompaniment system. And so naturally, the next step is, could the robot improvise with you? Could it compose the music? So that's how my research is now on the path of deep music generation. And when we want the agent to compose music for us, the good news is we have a lot of deep generative models already, VAE, GAN, transformer. So naturally, people develop music VAE, music GAN, music transformer, but we see a severe problem, which is at any time, right, when the music flows, there are many ways we can drive the music, and either it is conditioned on the previous bars to generate the future bars music, or conditioned on the melody, generate the chord, or vice versa. So we have something and we want to generate something else. There are many ways we can create music, but the traditional maximum likelihood training will sort of give us not a particular choice, but an average choice learned from this big data. And that is bad. And even worse is we do not have any control over the model usually. We can only sample from the model again and again. And as a musician, what we want is to be able to interpret the behavior of the model and furthermore, interact with the model once we can interpret it and control the generation. So in short, this generation via estimation methodology, there's a problem, and to solve it, I guess the solution is generation via representation disentanglement. So the philosophy here is fairly different. Actually, it's a lazy philosophy in a sense that we believe that nothing is new when we create music. It's just a recombination of existing components or factors. And we see similar issues when we, creating, even handwritten digits or human face. We not just want, randomly sample face from any distribution. We want to generate a face, for example, of certain hair color or age, or we know what digit we are trying to generate, or what kind of handwriting style that we want to generate. All right, so from a representation learning perspective, it is a non-trivial task. It's like machinists ask us, what is your requirement? And we humans say, learn the distribution and representation. But on top of that, the representations should make sense to our humans. And in the sense that we should be able to interpret the learned representation. And so far, we see the best way is to disentangle the learned representation into different parts, and so that we can name, okay, this part is that music factor, this part is another music factor. And once we can do that, we can do different ways to control the music generation. And how we're going to learn the interpretable representations is via various of inductive bias from music knowledge and psychological studies. All right, so that's kind of a brief introduction, and now I'm going to dive into the detailed studies. I'm going to start from monophonic study, and then polyphonic studies, multimodal representation learning, and finally come to the conclusion and future works. All right, so when I start to work on interpretable music representation learning, the only directly related work is actually music VAE from Google Magenta's team, so which is on the left hand. So we have a melody, and we have an encoder. We learn the Z. We have a decoder to reconstruct the music, but it's not disentangled and not interpretable because this just the only Z is here. So based on that, we developed something called a EC square VE, or explicitly constrained conditional VE. So the trick is actually pretty easy. We, after learning the Z, we just naively cut it into two halves. And we name the right-hand side, this part, as ZR, Z rhythm. And we couple it with the local rhythm decoder. So we're saying that, okay, this is the rhythm, and you should be able to recover the rhythm, just the rhythm of the music. And because if you have a MIDI, the rhythm is self-supervised, so we do not need extra labeling here. And actually, we do not have any explicit laws for pitch, which is ZP. We believe in that if we can separate ZR from Z, then for two measure music, the only meaningful factor left over is pitch. So here the model is we combine this decoded rhythm combined with the pitch to decode the final music, and that's it. And also to reduce the burden of the pitch, we add a chord condition. So now we have three controllable factors: chord, pitch, and rhythm. And this is a study published to ISMIR 2019. And let's see how well we can do on controllable representation learning and controllable music generation. All right, so here I'm showing you the original music. And it's in major, and here, just in the inference time, in the decoding time, I swap the chord to a minor chords. Okay, so that's in a minor key. Okay. And here is a more extreme example that I'm saying, what if I recompose the piece using this rhythm? All right, all 16 notes, and the original music is. Okay, so the generated piece is. All right, and finally, what if I use the pitch contour from this piece? This is coming up, going down. Okay, and the rhythm of this is almost all 8 notes. So this one will be. All right, so that's for monotonic interpretable music representation learning. And the lesson I learned is really, it's very like what I did on fixing the robot. The robot, to me, in the first demo, is a black box, and what I figure out is, okay, I should fix this ball, and other parts I just leave it as it is. And here, the only inductive bias, the explicit constraint is on the ZR. I have no constraint on ZP because I do not know how to explicitly constrain that. So the pitch contour is kind of a latent factor in our mind that we can kind of express using our natural language, but not using very precise symbol to characterize that. Okay, so there are two parts. One part you can specify, the other part you cannot. So you just leave it and let the black box system figure out on its own. All right, and now let's appreciate the demo when the controllable generation is combined with interactive performance system. Hi, Tail.
Hi, Gus. Long time no see. Hope your Music X lab is running well. In the last year, I learned some music style transfer techniques. Would you like to trade some bars with me?
A pleasure.
more complex. I can even make it more romantic and more jazzy.
All right, so I should pause and explain a little bit here. So it is trading fours with me. And when I'm playing, it's just doing accompaniment for me. And when I stop, it takes whatever I played and do style transfer on that. And by the way, all the dialogue are fake. I'm not an NLP guy, but all the music is real. And just now it's doing swapping using a more dense rhythm, and now it's just trying to shift the chord style. Okay. All right. I hope you like the demo, and I hope in the near future that this kind of agent can help us to play jazz. Okay. So now we're done with polyphonic music, and let's step into polyphonic music representation learning. And of course, I want to directly jump into how to disentangle the representation of polyphonic music. But before that, just at a time we want to do it, we figure out that the vanilla RNN model for polyphonic representation learning is not so effective. And we actually, so we have to first develop a without disentangle the representation learning model for polyphonic music. So the idea is that we develop a so-called piano tree VAE that learn the repetition of polyphonic music follow a tree structure. So the data structure is like as follows. We have notes on the bottom level, and we have simultaneous notes, middle level, and highest level is score. Okay, and here is just a graphical, more detailed view. And for each note, we have pitch and duration that encode in a binary sense. I should say this data structure is nothing new here, and we have a lot of this kind of tree structure for music. But the contribution here in this work is we developed a variational autoencoder that mirrors the structure of the data structure. That we developed a neural architecture for this. So the following this tree structure, the model is saying that okay, from bottom up, pitch duration encode to note embedding, and the note embedding encode to this simul note embedding, and finally the score. So here is an encoder, and the decoder kind of just mirrors this procedure. And this is a work we published to ISMIR 2020. And let's just briefly see how well it does on reconstruction. Say this is a piano roll of a piece. And the piano tree reconstruction is pretty good. And we see that, the red part is the duration is slightly not accurate, but overall it's good. But if we just use this 2D image piano roll plus an RNN model, it will be like this. So the reconstruction is bad because there's no inductive bias on, on the preference of the timing. And even worse, if I use MIDI image, which I flat it into the 1D sequence and use RN to encode and decode, it's even worse. I won't play it. Okay. It's just a nightmare. Okay. So how to better illustrate the learned repetition is useful and good. We do the latent Z interpolation. So we start from this piece, from this segment. and let the learned latent representation to smoothly traverse from this piece to this piece. So one is in F major, one is in B minor, so pretty far away. So let's listen to this latent Z interpolation. All right, it's pretty good, and we even see a walking bass here. And just as a comparison, here is using the piano roll representation to do the latent Z interpolation. Okay, I should stop here. So the idea is that if the latent Z is not well learned and you do the interpolation, it's just noodling around and we don't know what is going. And actually, at any point, it will suddenly shift to the second piece. So that's what happens. All right, and also we show some nice visualization. If we do Tisney and have this low dimensional or three-dimensional visualization, we can see the circle fifth, circle fourth, so on and so forth, in this latent space. All right, so now we have this well-learned latent representation for polyphonic music. We are now ready to disentangle it into two parts. So if we have pitch contour and rhythm for monophonic music, what are the correspondence in polyphonic music? The answer we came up with is chord and texture, right? So chord is like the pitch contour in a polyphonic version of pitch contour, and texture is the polyphonic version of rhythm. But now the only subtle difference is now the chord is something that we can explicitly control and specify using symbols, but texture is something that we cannot quite. So because of that, our solution, our neural architecture solution is like this. It has four parts. The most important part is the texture encoder, which is a CNN, treating the piano roll as input. I want to learn a rough sketch of the music, and we see that is the texture. Okay, so there's no explicit loss on that, but inductive bias is on this textural encoder. And we have this parallel chord encoder decoder. This is a chord VAE, and here we do have explicit chord progression loss for the learned Z chord. And finally, we combine the Z chord and Z texture together, feed that into a decoder. And here the decoder is the piano tree decoder that I just introduced. So there's a lot of inductive bias that's going on here. And this is also a study that we published to ISMIR 2020. I'm omitting, of course, a lot of details because, for the sake of time, actually, the more detailed graph look like this. All right, so let's listen to some demo. So now I have chord and texture. Of course, we can, recombine it, swap them. And this piece is rather long. So I'm showing you the score here. I'm going to, here's piece A, here is piece B, and here's piece C, or piece X. So this piece is using piece A's, piece A's texture and piece B's chord. So let's first listen to piece A. So the texture of piece A is thicker than peace B. You see that double tones? And here is clear cutoff. Here's another cutoff. All right, so now let's listen to piece B. And now listen to the chord progression, and the texture is way more sparse, I would say, compared to piece A. There's no cutoff, no, this double voicing. All right. So now let's listen to this, this mixed version, hybrid version. So the chord progression is following piece B. See that double voicing? And cut off. Yeah, cut off again. And yeah, so and here's a more demo. What we can do is fix the chord progression, but randomly sample in the texture space. There's more, I should stop. All right. So now, if we, combine this model with the previous model, what we have is Z pitch, Z rhythm, Z chord, Z texture. So if we feed those factors into a transformer, we are not, generating the piece note by notes, but we are generating the piece bar by bars and factors by factors, and I believe that is the more effective way to generate music. And here I want to show a demo that following this philosophy to do accompaniment generation. So here I have a melody here, and I feed this melody's latent repetition into a transformer, and then it's a long rest. And then here it comes back again, and I want to generate the accompaniment. The great part is when the melody comes to a rest, the accompaniment learns that I should fill in a secondary melody. See that? I think I should pause here and ask how long do we have? Is that already the time that I should stop the talk?
Hi, we have 9 minutes formally at least.
Okay, so maybe I should show the skip something that that I over prepared and just show this demo that this is an alma mater that we composed for ECNU. So we take the original melody and chord progression and use AI, the algorithm that I just showed, to compose both the piano accompaniment and the 4-part chorale. And so the texture for the accompaniment is borrowed from Chinese pop songs, and the texture for the crowd is for the singing part is borrowed from Bach's piece.
献给华师大校庆 composed by artificial intelligence, performed by Music X Lab.
All right, hope you like the music. And now let me just jump to the conclusion part and future work. So, we learn pitch, rhythm, texture, chord, and these are all, simple knowledge, I would say, in music theory. And in the future, I think I really hope that there's a unified model that we can learn all the music knowledges from low-level pitch and timbre to high-level, chord progression, rhythm pattern, texture, to even deep semantics like image, emotion, and motion. And I think the lesson I learned is when we build this model, that some part we can specify, and the explicitly specifiable parts can directly come from music knowledge. And so that's the right-hand part. That part, I guess, is hard, is somehow that we usually call it artificial intelligence, that grant stuff. But I'm not so worried about this, because as long as we can incorporate music knowledge into deep learning system, we can one day achieve that. What kind of worry me a little bit is on the left-hand side, is how we can learn fundamental perceptual level representations like pitch and timbre, beat, key, without music knowledge, but purely in a data-driven way. And for that part, I guess we need a certain amount of self-reflect and just think of why we humans do that, and that's kind of analogous to the human stupidity part I did, that we really have to step back and do self-reflection. And so I guess the answer that hidden in this part is deeply connected to the core of unsupervised learning. So how do we just rely on the data and learn the fundamental music concepts? And I believe that the answer is kind of hidden somehow in theoretical physics, in a sense that we human tend to over disentangle the representations. Actually, the starting point, the ending point is maybe the starting point, in the sense that disentanglement is kind of a built-in inductive bias in our human mind. Just think of, why do we have the concept of timer and pitch? And this is very analogous to how do we have the concept of time and space. And in theoretical physics, we know that we perceive time and space because of symmetry, because of, if I'm at Shanghai or C4DM, or if I'm today or yesterday, I will observe the same physical law. And analogously, if I shift the pitch, if I shift the timer, I will observe the same music theory. And this kind of thought is deeply built in the symmetry theory. So we also know that human mind tend to over disentangle stuff. For example, if everything is low speed, we observe the Newtonian law. But we know that relative theory is there. It's just like, when we move so fast, the time gets twisted. And similarly, in classical music, we know that if we just shift the pitch, the timer won't change, because the music is such a narrow range. But in electronic music, we know it's not the case. So maybe we can inject symmetry into representation learning, and that can help us learn the fundamental level of interpretable music representations. So that's the future work, and actually we are doing that. We did some simple thing that we learn from the trajectories of the balls. And if we just want to build a VAE and say, what is the XYZ, the 3D coordinates, that's impossible. But if we inject symmetry into this model somehow, it can learn something like this 3D coordinates. One is X, one is Y, one is Z. So we are on this path, and hopefully in the future, what we can do is to build all this knowledge from a data-driven bottom-up way. All right, so that's the end of my talk. Last but not least, all the work is always done by my great students. I'm just here taking most of the credits. Thank you.